So before we go any further, we're going to do this example problem first. And it says draw 1, 2, 3, 4, 5, 6 hexamethyl cyclohexane with all the methyl groups in the axials and then all the methyl groups in the equatorials. All right, so we now know at this point that cyclohexane's a little bit strange versus a normal straight chain molecule because it's somewhat locked into position. It can flip between boat and chair, but on each carbon, there is two special types of bonds, one that we call the axial bond and one that we call equatorial bond. All right, so this is just going to prove that I know the difference between the two. All right, so cyclohexane is there. And then 1, 2, 3, 4, 5, and 6 hexamethyl. So there's a methyl group on every one of those carbons. All right, so part A wants me to draw cyclohexane. So here we go. There's the cyclohexane structure. And they want me to draw all the methyl groups in the axial positions first. All right, so axial positions I know go straight up and straight down. All right, so here, straight up, straight down, straight up, straight down, straight up, and straight down. And now I need to go through and draw CH3s on them. So this allows me to show a notation of the bonds that I'm targeting because these are a little bit different than a straight chain. These are in a ring. They have two different types of bonds. And if I'm focused on the axial positions, then all of these methyl groups are sticking up on flagpoles. And they're all going all the way around the molecule, either straight up or straight down on opposite sides of that ring molecule. Okay? All right, so for the next one, it tells me to do the same thing, but this time it wants me to go through and draw them on equatorial bonds, not axial bonds. All right, so equatorial bonds. Look at what I did up here. I drew the axial straight up, right? So that means here I'm going to draw my equatorial out and slightly down, and then slightly up, then slightly down, then slightly up, then slightly down, and then slightly up. And then I go through and I draw CH3s on all of them. All right, so there is my proof that I know the difference between an axial and an equatorial bond. Now here's the story with axial and equatorial. Out of these two, molecules like to spread their wings. Molecules really like to take up as much space as they can. They love to spread their wings and take control over the most land as possible. And for that reason, equatorials are always the most stable type of bond when we begin to look at these two different things. So out of these two versions, this one that has all of the methyl groups in the equatorial position is going to be much more stable than the methyl groups that are out on flagpoles for the molecule to say, hey, here it is, come and get it. They don't want that, right? Stability is keeping it the way that it is. It's not very reactive. It's not going to do anything for me. It's just going to be the same, and it's dependable, and it's always going to be there. When they start putting these methyl groups on the flagpoles, then these things are sticking out like sore thumbs, and other reagents can come in and react with them and change them and destroy them. So out of these two, equatorial bonds are going to be the most stable, and they're also the preferred way to draw the bonds in cyclohexane. All right. So we've also talked about this idea that this will flip. Okay, so for instance, if I took this cyclohexane to the left and I flipped it up, all right, I will get a boat position. And then I could take this one and flip that side down, and that will give me basically the chair position again. So when these things begin to flip on me, a ring flip could happen. And when ring flips happen, what that basically means is that the axial bonds will go to equatorial bonds, and the equatorial bonds will then go to axial bonds. So ring flip could be a problem. And when ring flip happens, all of the orientations of my bonds begin to change. So they go backward. So what this basically means is that if I get a large group onto a cyclohexane ring, and that large group comes in and it goes to an axial bond, that molecule will look at that big piece that has just made its way in and attached itself, and it goes, oh, no, this ain't going to work for me, because this large group is on an axial bond, and I am very stable if things are equatorial. So this carbon gets pushed up, the ring does it, this carbon gets pushed down, a ring flip happens, and it changes this axial position, boink, over to an equatorial position. And this is how the molecule will self-stabilize itself. So when you're putting groups onto a ring, that will happen a little bit later on in the semester in a different lecture module, you need to keep this in mind. If given the chance, the rings will self-correct. The rings will come in, and they will take these larger groups that you're trying to put on them that they have received, and if they go on an axial position, they will ring flip themselves, and they will just literally take one piece, flip it up, take the other end, flip it down. That's a ring flip. And that changes the order of every single bond. So as you notice here, the blue dots, all of these are equatorial bonds. They go slightly out and up and slightly out and down, right? So when ring flip begins to happen, look at where the blue dots go. They now go fully up, or they now go fully down. And that means that my equatorial bonds, because of the ring flip, have now changed to axial bonds and vice versa. Okay, so that is how these rings will fix the corrections or the mistakes that begin to happen with them. And that means that they do change position if you are not careful and if you decide not to track them. Here's an example of a group that's actually on a ring. So what I see to the left is going to be a chair conformer, and this is the methyl group in the equatorial position, right? I see that. It's not fully up or fully down. This is slightly out and down, okay? So this is an equatorial position. A ring flip could happen, though. So this piece will be pulled up, and this piece will be pulled down. Ding, ding. You see those opposite directions? And when that begins to happen, then my equatorial bond now changes into an axial bond. So that methyl group is now pointed straight down on what we would refer to as an axial bond. This is the least stable out of the two. So if given an opportunity, the ring will flip back and it will gravitate toward this conformer. So it really likes the chair conformer that has the groups, the largest groups at least, on the equatorial positions. So we still get the flip and flop back and forth, back and forth, back and forth. That still happens. Hundreds of thousands of times a second is how fast it happens. But out of the two, it prefers the left-hand side over the right-hand side. I know this is a little elementary, but I think it gets the point across. Here in the front with the lady, that's the chair position. Notice she's sunbathing in her bikini, and she's out laying out into the sun, all nice and happy, waving at the guy in the boat. And this is the difference between the chair and the boat conformer of cyclohexane. Okay, so we've talked about being able to go from one to the other, and this flip begins to happen, and that means we also include a boat in that description as well. So here's another elementary diagram of energy and the stabilities as far as cyclohexane's concerned. And over here to the left, you're seeing that this is a chair conformer, and this has the lowest energy that's out there. The reason that this is a good thing is because low energy means extremely stable. The more energetic they are, the more active they are, the more chances of them getting in trouble. So if you have a person that likes to stay home and has very low energy, doesn't want to get out, doesn't want to socialize, stays out of trouble, those are very stable children, and those are very stable molecules as well. However, the more energy that they have, the more chances of them getting out and finding themselves getting into trouble, well, those odds go up. So the higher energy, the more unstable that those children become, and the more unstable those molecules become. So here we have a chair position, and this goes to what we call a half chair. So this is in the terms of a ring flip. So one piece gets flipped up, the other one doesn't get touched. And then we have what we call a twist boat. They don't even bother drawing that depiction or that diagram. And then if we continue to push it up, then this goes into a full-blown boat molecule or conformer. All right. Then we can take the other end, slightly start pulling it down. This goes back to a half chair, and then we can continue to pull it down, and then that's when we can go to a chair, but it's the mirror image of the first one, right? And this is what we call the ring flipping. So the chair to the left and the chair to the right are both chairs, but they are mirror images of each other, which means that all of our axial bonds go to equatorial bonds here and vice versa. That is why that flip begins to happen. Okay, something else, I've already kind of mentioned it, but I do think it's worth repeating because we're going to start to see these in some of the example problems. But when things are attached to that particular ring, to the cyclohexane ring, we want to make sure that the largest groups go into an equatorial position whenever possible. All right. The reason for that is the equatorials are the most stable, and the largest groups need to go into the most stable conformer. So that's the reason that they orient themselves the way that they can. So if we're given a choice, and we're given a couple of different pictures, and we're told pick out the one that's the most stable out of these three, then this is something that we look for. We look for equatorial bonds. We look for how many equatorial bonds. We look for what's on those equatorial bonds, because the largest groups need to go on the equatorial positions whenever possible. All right. If not, we probably need to flip the ring. And that means flipping the orientation of every single bond that's on that structure to make sure that the largest group does in fact go on the equatorial position. All right, we do not like axial. Okay, now, before we do any examples, a couple of more terms that we need to introduce here before we go to the next video. And now that we've talked about axial, now that we've talked about equatorial, with each one of these bonds, we kept referring to up and we kept referring to down. Did you catch that? Axial bonds, up, down, up, down, up, down, up, down. Equatorial bonds, they're out and they're slightly up, slightly down, slightly up, slightly down, slightly up, slightly down. So there's a reason that I did that, and that's because I want you to start paying attention to the orientation of how they are directed. Because there's some terminology that comes into play here. And the terminology is something that we call cis and something that we call trans. For a cis prefix, this means that the groups are pointed in the same direction. For a trans prefix, that means the groups are going to be pointed in opposite directions. what this means is that on a cyclohexane ring, if I'm putting groups on there and they want me to get super particular and talk about these axial and equatorial bonds, and they want me to be particular and talk about cis and trans, then what they want me to do is they want me to look at these groups that they have placed onto this ring. And they're kind of locked into place in a way. And if those groups are both pointed in the same direction, both of them are pointed up, or both of them are pointed down, then we have a cis orientation assigned to those groups. For the trans, they need to be opposite. Notice that has nothing to do with axial or equatorial. That's another common problem that people make. They think cis means the same type of bond. If both of them are axial, then it's going to be cis. Or if both of them are equatorial, then it needs to be cis. No. That is not right. You need to delete that from your brain. Cis has everything to do with position. It has nothing to do with axial and equatorial. Quite honestly, nothing to do with it at all. You don't even look at whether or not they're axial or equatorial to make this decision. The only thing that you need to be looking at to make this decision is the direction of which they're pointed. Now, axial and equatorial does have a role that they play. But the only thing that I need to take into consideration is how those groups are oriented. Are they both pointed up? Are they both pointed down? Or are they pointed in opposite directions? That is the only thing that brings into the determination of whether these things are going to be labeled as a cis or as a trans group. All right, so let's take a look at maybe an example. Is the conformer of 1,2-dimethyl cyclohexane with one methyl group in an equatorial position and the other in an axial position the cis or the trans isomer? How do we solve this type of problem? Well, notice I told you, you only look at the direction of the groups. And this is going to be pretty easy because they gave me the structure. They did not want me to draw it. Sometimes they'll want me to draw it from scratch. And I'll have to start there just in order to make this determination. But at least here they gave me the structure of it. So this methyl group that's right here, this is on an axial position and this points straight down, right? I can clearly see that. It points straight down. And then for this methyl group, this is on the equatorial bond. I see that coming out. But look at that. It's coming out and slightly down, isn't it? And I know that it's down because this axial is pointed straight up. So just like we talked about before, maybe in the past video, that if the axial goes straight up, the equatorial goes slightly down. And in here, this axial goes straight down. This equatorial, which is the hydrogen, goes slightly up. They're opposite of each other. So these two methyl groups, this one points straight down, this equatorial points downward. They're both in the down position, and because of that, they are on the same direction, pointed in the same way, and we call this the cis isomer. That is how we solve those types of problems. All right? So it's all about direction. That's all that it's about. It has nothing to do with axial or equatorial to make this decision with. You need direction. That's what you need to look at. All right? Over to the left-hand side, you'll see another example of a cyclohexane ring with two methyl groups. Notice that the first methyl group to the left points straight down, so this one goes down. And then this methyl group, it points out in the equatorial position, but it's also slightly down. All right, so because both of these are slightly pointed down and one fully down, this is going to be the cis isomer of that particular structure. All right, now if we flip it and just change the position, look at what they did here. The only thing that they did is take this methyl group and put it here and take that hydrogen and put it there. That's the only change that they made in this structure. That's it, folks. That's all. But yet we name it completely different because it is a different structure. They have different properties, believe it or not. So if I take a look at this, Well, I can see that this is equatorial, but it's slightly pointed up. And this is equatorial, and it's slightly pointed down. So because one's slightly pointed up and one's slightly pointed down, this is going to be the trans orientation here. In addition to that, both of these groups are equatorial. So therefore, this one is the more stable version of the molecule out of the two choices that I see on the screen. So that doesn't happen every single time. Trans is not the most stable every single time. But what does happen every single time are the groups, the most groups in the equatorial positions are going to be the best favored product or reagent that will, of course, be the most stable. All right, so if I take a look at another example, here's another one. It says, which is more stable? Here's a cis 1,4-dimethylcyclohexane in each case, but they have the orientation in a different way for me. All right, so here I see a methyl group in an axial, and I see a methyl group in an equatorial. And then here I see a methyl group in equatorial, and I see a methyl group in axial. Which is more stable? Well, if the left-hand side has a methyl pointed down on axial and a methyl that's on equatorial, and the right-hand side has a methyl on the axial and a methyl on the equatorial, then, folks, these two things are the same. There is no difference between these. Neither one of these is more stable than the other one. They both have the same stability because it's the same freaking molecule. Now, axial points down, so this is down. And then this equatorial is out and slightly down, so this is down. They both point down, which is why this is a cis. Over here on this side, same story. This axial points down. This equatorial points slightly down. They both point in the same direction, so that's a cis. The 1,4 number, where does that come from? Well, on carbon number 1, I have a methyl group, and then this could be carbon number 2, and carbon number 3, and carbon number 4. I have another methyl group. So that's why this is a 1,4-dimethyl. And of course, hopefully you know why we call it a cyclohexane. If not, you need to go back to the lecture. Very first video of the lecture. All right, here's another one. Which is more stable? Here I get two versions of a trans. We'll take a look at them. Here I get a methyl group on equatorial that points slightly up. And here I get a equatorial that points slightly down. So this is slightly up and this is slightly down. They're in opposite directions. So this is a trans. That methyl group is equatorial. This methyl group is equatorial. All right, then over here on this side, I see this methyl group pointed straight up and this methyl group pointed straight down. They're opposite directions, so therefore it's trans one more time. But in this case, they're both on the axial position. So out of these two, the one on the equatorial positions are going to be more stable, and there is a clear difference between these. These are not the same molecule here. I know it's the same carbon, the same hydrogens, the same type of bonding, but the directions are different. And those directions could mean a world of difference in the field of organic chemistry. All right, so the one to the left, the equatorial version, is going to be the most stable because those methyl groups are on the equatorial positions. Both of them are on equatorial. And then what I would see on the right-hand side are axial. Those are the flagpoles. We don't want things sticking up on flagpoles. It's like a white flag that says, come and destroy it, because it's less stable. All right. So that's where this video is going to stop. We're not quite yet done, though. We're almost. The next video, I think we'll be able to get it finished. So what I want to do in the next video is take this idea, now that we're more familiar with the cyclohexane ring and about cis and trans and axial and equatorial bonds and which one's more stable than the other, I want to take it another step further, and I want to talk about nomenclature. I want to talk about naming these things. So, for instance, I want to do a few examples on how they derive this name down here at the very bottom. If I give you a structure that looks like this, would you be able to give me a name that looks like this one? That is what the next video is going to focus on. Again, I don't want to take anything for granted, so we're going to be doing some example problems of that, and that's what you'll find out next. So stay tuned. There's probably just one, maybe two, if even that, left in this whole lecture module, and you are finished with it. So you might as well just bite the bullet and go ahead and watch me for the next 20 to 25 minutes and go ahead and finish it and call it a day. And then we both can go celebrate.